Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Today, we're investigating something that sounds almost too good to be true. Complete observability coverage. Every HTTP request, every database query, every gRPC call, without touching a single line of application code.
And here's the kicker. Under 2% CPU overhead, when traditional APM agents can add significant overhead to your compute just to tell you what's happening.
So either this is a massive breakthrough, or there's a catch nobody's talking about. Let's find out which.
The technology is eBPF-based instrumentation for OpenTelemetry. And to understand why this matters, we need to start with the problem it's solving.
The instrumentation gap. In many enterprises, a significant portion of services have limited or no observability coverage.
Exactly. And it's not because teams don't want observability. It's because SDK instrumentation is genuinely painful. You're looking at importing libraries, wrapping function calls, propagating context across service boundaries. For a polyglot environment with 50 services across Go, Java, Python, Node, that's weeks of work.
And that's assuming you even have access to the source code. What about third-party binaries, legacy services nobody wants to touch?
Those become permanent blind spots, and every blind spot is a potential 3 a.m. incident where you're flying completely blind.
So teams make a trade-off. They instrument the critical paths and accept gaps everywhere else.
Right? And then they compound the problem with APM agents that add significant CPU overhead. Now your high-performance services can't use them at all, so your fastest, most critical paths become your biggest blind spots.
It's a genuinely impossible choice. Coverage or performance? Pick one.
Which is exactly what makes eBPF instrumentation so interesting. It sidesteps this entire trade-off.
Okay, so how does it actually work? Because kernel-level instrumentation sounds like magic hand-waving.
It's not magic, but it is genuinely clever. So eBPF, Extended Berkeley Packet Filter, lets you run sandboxed programs inside the kernel. These programs can attach to kernel functions, like syscalls, network stack operations, file system calls.
Wait, you're executing code in kernel space? How is that not a massive security risk?
Because every eBPF program goes through a verifier before it can run. The verifier is incredibly strict. It proves mathematically that your program will terminate, won't access invalid memory, won't crash the kernel. If verification fails, the program simply doesn't load.
So the kernel itself is guaranteeing safety.
Exactly. And once verified, it gets jet compiled to native machine code for performance. Then it attaches to specific kernel hooks and executes whenever those hooks fire.
Give me a concrete example. My Go service makes an HTTP call. What actually happens?
Your Go service calls the standard library, which eventually makes a syscall to the kernel's network stack. At that point, an eBPF probe attached to the socket operations captures the packet metadata. It extracts HTTP information, method, path, header, status code, from the raw bytes, stores that in an eBPF map, which is a data structure shared between kernel and user space. A collector running in user space reads from those maps and converts everything into OpenTelemetry spans.
So the eBPF program is just observing operations that are already happening. It's not adding new work.
That's the key insight. The kernel is already processing these syscalls, already handling these network packets. The eBPF probe adds nanoseconds of overhead to observe what's already happening. That's why you get under 2% CPU impact.
Compared to APM agents that have to intercept at the application level, wrap every function call, maintain their own context propagation.
Right. Traditional agents are doing a lot of work in user space. eBPF just watches the kernel do work it was already doing.
This sounds like it's been possible for years. Why is it suddenly relevant?
Because of what happened in May 2025, Grafana donated their Bela project to the OpenTelemetry project. Bela was already one of the most mature eBPF instrumentation tools, and now it's becoming the official OpenTelemetry eBPF instrumentation.
So this went from interesting experimental tool to core part of the OpenTelemetry ecosystem.
Exactly. You've got the weight of OpenTelemetry behind it now. The governance, the community, the integration with collectors and backends. This is no longer a side project.
What does deployment actually look like?
Daemon set on Kubernetes. You deploy one pod per node. It automatically discovers all processes on that node and starts generating telemetry. Zero changes to your applications, zero configuration for each service.
So you go from limited coverage to 100% in, what, an hour?
That's what teams are reporting. Deploy the daemon set, configure your collector endpoint, and suddenly you have spans for every service on every node. Services you forgot existed are now visible.
Okay, I need to poke at this. What's the catch?
There are real limitations, and the biggest one is context. eBPF captures at the protocol level, HTTP, gRPC, SQL. It sees the wire format. It doesn't see your application's internal state.
Meaning what specifically?
Meaning, it can tell you, post request to /API/orders, 200 response, took 47 milliseconds. It cannot tell you, this was customer ID 1234, using feature flag new checkout, for order value $500.
So you get the technical telemetry, but not the business context?
Exactly. Any attribute that exists only in your application's memory, user IDs, tenant identifiers, feature flags, business metrics, eBPF can't access them. It only sees what crosses the kernel boundary.
Which means for business-critical paths where you need that context for debugging or analytics, you still need SDK instrumentation.
Right. eBPF isn't replacing SDKs. It's providing a universal baseline that SDKs enhance.
What about encryption? If everything's TLS, doesn't eBPF just see encrypted bytes?
This is the other major limitation. TLS encryption happens before data hits the kernel network stack. So yes, eBPF sees encrypted packets it can't parse.
So this zero configuration story breaks down for anything using HTTPS.
There are solutions, but they add complexity. The most common is uprobes on OpenSSL or Boring SSL. You hook the encryption libraries before they encrypt. But now you're dependent on specific library versions, and it's language specific.
So much for any language, any framework.
For TLS, yeah. The other approach is service mesh integration. If you're running Istio or Cilium, they're already terminating TLS at the proxy layer. eBPF can observe the unencrypted traffic between proxy and application.
Which means you need either library-specific hooks or a service mesh. The zero configuration story has asterisks.
Absolutely. TLS handling is the main complexity in production eBPF deployments. Teams need to plan for it.
Let's talk about protocol support. You mentioned HTTP and gRPC. What else?
HTTP 1.1, HTTP 2, gRPC, Redis, and SQL, including Postgres and MySQL. Those are the protocols with mature support today.
What if I have a custom protocol, some internal RPC format?
Then you need SDK instrumentation. eBPF parses protocols it knows. If it doesn't recognize the wire format, it can't extract meaningful telemetry.
So you're covered for standard protocols, but anything custom is a gap.
Right. And that's actually fine for most teams. The standard protocols cover 80 to 90% of service communication. You fill gaps with targeted SDK work.
Okay, so let's synthesize this. How should teams actually think about eBPF versus SDKs?
They're complementary layers, not competing approaches. eBPF gives you the baseline, universal coverage, zero-touch deployment, minimal overhead. SDKs give you depth, business context, custom spans, application-specific metrics.
So you'd run both?
In production, almost always. eBPF for the foundation, SDK instrumentation for business-critical path where you need that application context.
Give me a decision framework. When do I go eBPF first versus SDK first?
eBPF first makes sense when you have a polyglot environment and can't standardize on one SDK. You need coverage fast and can't wait for instrumentation work. You have performance-critical services that can't tolerate agent overhead, or you have legacy and third-party binaries you can't modify.
And when do I reach for SDKs?
When you need business context, user IDs, tenant info, feature flags. When you need custom spans for business logic that doesn't cross network boundaries. When you need application-specific metrics that only exist in your code.
And realistically, most teams will need both.
Exactly. The question isn't which, it's what ratio. Some teams are 90% eBPF with SDK only for their core revenue paths. Others are 50-50. It depends on how much business context matters for your debugging and analytics.
What does the maturity path look like?
Week 1. Deploy the OpenTelemetry eBPF operator on a non-production cluster. Validate it's capturing the protocols you care about. Get comfortable with the deployment model.
And then?
Week 2. Production deployment. You'll immediately have baseline coverage everywhere. Identify which services actually need business context. Usually it's your top 3 to 5 revenue-generating paths.
Then add SDK instrumentation just for those paths.
Right. You're not instrumenting everything with SDKs anymore. You're instrumenting strategically only where the business context matters for debugging or analytics.
So the total instrumentation work drops dramatically.
Instead of instrumenting 50 services with SDKs, you're instrumenting 5. eBPF handles the other 45.
What about the organizational impact? This changes how platform teams operate.
It shifts the work from instrument everything to curate what matters. Platform teams become observability curators rather than instrumentation mechanics.
And application teams.
They get observability for free. No SDK imports, no instrumentation work, no context propagation bugs. They can focus on shipping features. If they need business context for debugging, they add targeted SDK spans, but that's their choice, not a prerequisite for visibility.
Let's bring this back to the original question. Is eBPF instrumentation too good to be true?
The core promise is real. Under 2% overhead, zero-code deployment, instant coverage, that all works. But it's not a complete replacement for SDK instrumentation.
It's a foundation that makes SDK instrumentation optional rather than mandatory.
Exactly. You go from, we have to instrument everything, to, we can instrument what matters. That's a fundamental shift in how observability programs work.
And the May 2025 donation to OpenTelemetry means this is now mainstream infrastructure, not experimental tooling.
Right. This is the observability stack consolidating. OpenTelemetry for the standard, eBPF for zero-touch collection, SDKs for business context. The pieces are coming together.
Practical takeaway for listeners.
Start with eBPF for your baseline. Deploy the OpenTelemetry eBPF operator, get instant visibility into everything. Then add SDK instrumentation only where you need business context. You'll go from limited coverage to 100% in hours, then enhance critical paths over weeks instead of months.
From we can't instrument everything to zero code coverage in minutes.
With the kernel doing the heavy lifting.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.